Welcome to Lab of Lad. You've joined us today for a deep dive, and we're going to be talking about electrostatics.
Right.
It's, you think about those little sparks, in life.
Right.
A balloon sticks to your hair.
Yeah.
Or even, as we discovered in the source material,
Yeah.
how ink can be precisely jetted onto things like food cans
Oh, wow.
and even eggs.
Huh. Interesting.
So our mission today is to really unpack the core ideas of electric charge,
Okay.
what makes materials conductive,
Yeah.
and the law that governs the forces between charges,
Okay.
Coulomb's law.
Right.
And we're aiming for, just a relaxed, friendly chat,
Sure.
like we're just catching up in a cafe.
Yeah.
No confusing science speak.
Okay.
Just clear concepts,
Right.
maybe a few laughs, and definitely some of those aha moments.
Sounds good.
So buckle up as we explore Karga, conductors, and Lily Coulomb.
Absolutely. And, it's worth underscoring just how foundational these concepts are.
Right.
As the source material beautifully lays out. Electricity isn't just about static cling.
Right.
It's a force, a primary force.
Right.
That underpins, the structure of matter itself.
Yeah.
It's the glue that holds atoms together,
Right.
forms molecules, and dictates how they interact. It's the very basis of chemistry.
Right.
And in turn, life.
Yeah.
Quite a contrast to gravity, which, while dominant on cosmic scales, plays a much smaller role in this microscopic world.
Right. Yeah.
Governed by these electrical forces.
Gravity keeps our feet on the ground, but electricity is what makes the ground itself solid.
Right.
Speaking of foundations, our guide also gives us this, neat little historical peek.
Yeah.
It wasn't until the 19th century
Right.
that scientists like Ørsted,
Uh-huh.
Faraday,
Yeah.
Henry,
Right.
and the brilliant Maxwell connected the dots
Yeah.
between electricity and magnetism, realizing they're two facets of the same electromagnetic force.
Right.
Pretty cool to think about.
Yeah.
Okay, let's dive into our first big idea,
Sure.
electric charge.
Consider those, familiar scenarios again.
Right.
Socks fresh out of the dryer,
Yeah.
clinging to your shirt,
Huh.
sometimes with a little crackling sound,
Right.
or a plastic comb that, after running through your hair,
Yeah.
can mysteriously bend a thin stream of water.
Right.
Our source even gives that surprising example of industrial printers using electrostatic principles for incredibly precise applications.
Right.
Including printing on things like, food cans.
Right.
And yes, even coding information onto the surface of eggs.
Eggs.
Yeah.
Still stuck on that.
It's pretty remarkable.
It makes you realize that electric force, just like gravity,
Mm-hmm.
is a fundamental way that things interact.
Right.
And here's something that really clicked for me from the source. These electric interactions
Yeah.
are actually the root cause
I-
of so many other forces we experience daily.
Right.
Think about the normal force,
Mm-hmm.
the feeling of solid ground beneath your feet.
Right.
That's ultimately due to the electric repulsion between the atoms in your feet and the atoms in the ground.
Yes. Yeah.
Friction, tension in a rope, all down to these underlying electrical forces at the atomic level.
Precisely. Now, how do objects actually acquire this electric charge, becoming, quote-unquote, electrified?
Right.
The most straightforward way is through friction.
Right.
Simply rubbing two different materials together.
Okay.
Remember rubbing your shoes on a wool carpet and getting that little shock
Right.
when you touch a doorknob?
Yeah.
That zap is the discharge of built-up electric charge.
Okay.
Our source points out that these effects are much more pronounced on dry days. Why do you suppose that is?
I'm guessing it's because the humidity in the air acts like a sponge for charge.
Right, exactly.
It allows the excess charge to leak away more easily,
Right.
preventing it from building up to the point where you get a noticeable shock,
Right.
like a tiny atmospheric escape route for electrons.
Exactly. Water molecules in the air can indeed facilitate the movement of charge away from an object.
Okay.
Now let's talk about the types of charge.
Right.
Benjamin Franklin, in his wisdom, proposed that there are two kinds of electric charge,
Right.
which he arbitrarily named positive and negative.
Okay.
Today, we understand that these are associated with fundamental particles.
Right.
Electrons carry a negative charge, and protons carry a positive charge.
The yin and yang of the electric world.
Indeed.
And our guide revisits those classic experiments. You
Right.
probably all saw in science class,
Mm-hmm.
rubbing a rubber rod with fur
Yeah,
and a glass rod with silk.
right.
Those always seemed like magic.
They're beautifully illustrative. When you rub a rubber rod with fur, electrons are transferred from the fur to the rod,
Right.
giving the rubber rod a net negative charge.
Okay.
Now, if you bring that negatively charged rod near another negatively charged rubber rod,
Right.
what do you predict will happen?
They would definitely push each other away, right?
Yes.
Like trying to force two north poles of magnets together.
Exactly.
But if you bring that negatively charged rubber rod near a glass rod that has been rubbed with silk,
Right.
which ends up positive
Uh-huh.
because it loses electrons, they'll attract.
Right.
Opposites do indeed attract,
They do.
electrically speaking.
Electrically speaking, yes.
And figure 22.2 in our source clearly depicts this according to Franklin's original convention.
Exactly. And this leads us to a fundamental principle.
Right.
Law of conservation of electric charge.
Okay.
When we charge objects by rubbing them, we're not creating charge out of nothing. Instead, we're simply transferring charge from one object to another.
Okay.
The total amount of electric charge in a closed system always remains constant.
So in the glass and silk example, electrons move from the glass to the silk.
Right.
The silk becomes negatively charged,
Right.
and the glass becomes equally positively charged.
Exactly.
One gained what the other lost, as shown in figure 22.3.
Yes.
Same amount of charge, just redistributed.
Yes.
And with the rubber and fur,
Right.
electrons hop from the fur onto the rubber.
Yes.
It's all about this exchange,
Right.
this cosmic accounting of charge.
Precisely. And it gets even more fundamental.
Okay.
In the early 20th century, Robert Millikan,
Yeah.
his famous oil drop experiment, revealed that electric charge isn't infinitely divisible.
Right.
It's quantized.
Okay.
This means that any electric charge you find will always be a whole number multiple
Right.
of a basic unit of charge,
Okay.
the elementary charge, denoted by E.
Right.
So any charge Q is given by Q equals plus or minus N times E,
Right.
where N is an integer.
The smallest unit of charge.
Exactly.
And our guide gives us that incredibly tiny value.
All right.
1.60 co-18 times 10 to the minus 19 coulombs.
That's it.
So a single electron has a charge of minus E.
Right.
A single proton has a plus E.
Yeah.
And those neutral neutrons.
Right.
Well, they have zero charge.
Right.
It's like charge comes in these indivisible little packets.
Yeah.
Like atoms of electricity.
That's an excellent analogy. Now, to test your understanding of these charge interactions, let's consider quick quiz 22.1.
Okay.
We have three objects, A, B, and C.
Right.
We observe that A and B repel each other.
Okay.
And B and C also repel each other.
Right.
What can we definitively conclude about the charges of A and C?
Okay, let's think this through.
Sure.
If A and B repel,
Uh-huh.
they must have the same type of charge.
Okay.
Either both positive or both negative.
Right. Similarly, since B and C repel, they must also share the same type of charge.
Right.
So if B is positive,
Right.
then air is positive,
Right.
and C is positive.
Right.
If B is negative,
Uh-huh.
then A is negative, and
Right.
C is negative.
Right.
In either scenario, A and C must have charges of the same sign.
Yes.
So the answer is that A and C have charges of the same sign.
Correct. Now let's shift our focus to how different materials behave
Right.
in the presence of these charges.
Okay.
We can broadly classify materials
Right.
based on their ability to allow electric charge to move through them.
The classic showdown. Conductors versus insulators.
Exactly.
This is where the rubber meets the electrostatic road, so to speak.
Exactly. Conductors are materials in which some of the electrons are not bound to individual atoms
Okay.
and are free to move throughout the material.
Right.
Metals like copper,
Uh-huh.
aluminum, and silver are excellent examples.
Right. If you introduce a charge to one part of a conductor, these free electrons will quickly redistribute themselves across the entire surface.
Okay.
Think of it like a crowd of people in a large room.
Right.
If you push some in one corner, they'll quickly spread out.
That makes perfect sense.
Yeah.
They're like super mobile network of charge carriers constantly shifting and adjusting.
Right.
And on the other hand, we have insulators,
Right.
materials like glass,
Yeah.
rubber, and dry wood.
Right.
In these materials, the electrons are tightly bound to their atoms
Right.
and aren't free to roam.
Right.
So you charge an insulator by rubbing it, that charge tends to stay localized in the area that was rubbed.
Right.
It can't easily spread throughout the material.
That's right. Only the immediate area of contact experiences a significant charge buildup.
Okay.
Then we have the intriguing in-betweeners,
Mhm.
semiconductors like silicon and germanium. Their electrical conductivity lies somewhere between that of conductors and insulators.
Right.
What's truly remarkable is that we can precisely control their conductivity
Right.
by adding tiny amounts of impurities.
Okay.
This ability to fine-tune their electrical behavior is what makes them indispensable in modern electronics. They're the fundamental building blocks of transistors and computer chips.
Okay, so we've got these different types of materials.
Right.
Now, here's a question that always intrigued me.
Yeah.
How can you charge a conductor without actually touching it
Right.
with a charged object?
Right.
It sounds a bit like electrostatic telekinesis.
It's a clever phenomenon called charging by induction.
Okay.
Imagine a neutral conducting sphere
Okay.
that's insulated from the ground.
Right.
It contains an equal number of positive ions
Right.
and free electrons.
Okay.
So its net charge is 0. You bring a negatively charged rubber rod near the sphere,
Right.
but you don't make physical contact.
Okay.
What happens to those free electrons within the sphere?
They'd feel a repulsive force
Uh-huh.
from the nearby negative rod
Right.
and try to get as far away as possible. Right?
Exactly.
So they would migrate to the side of the sphere farthest from the rod,
Right.
leaving the side closest to the rod with a surplus of positive charge due to the stationary positive ions.
Exactly.
Figure 22.4 in our source illustrates this charge separation beautifully.
Exactly. Now, here's the key step in induction.
Okay.
If we momentarily connect the sphere to the ground using a conducting wire,
Right.
some of those excess electrons that have been repelled to the far side
Right.
will actually flow away from the sphere and
Wow.
into the Earth.
Okay.
The Earth acts as a massive reservoir for charge,
Right.
capable of accepting or supplying virtually unlimited amount. Right.
Without significantly changing its own electrical potential.
So we've given those unwanted electrons an escape route.
Right.
Now, what happens when we disconnect the ground wire
Right.
while the negatively charged rod is still held nearby?
The sphere is now left with a net positive charge.
Okay.
Because it has lost some of its electrons.
Okay.
Finally, when you remove the negatively charged rubber rod, this induced positive charge will redistribute itself uniformly across the entire surface of the conducting sphere
Right.
due to the mutual repulsion of the positive charges.
Right.
And there you have it.
Okay.
A positively charged sphere
Right.
without ever having touched it
Right.
with a positive object.
Right. Yeah.
This is distinct from charging by conduction,
Right.
which requires direct physical contact
Right.
and charge transfer.
That's so elegant. The charged rod is just influencing the existing charges within the sphere from a distance.
And our guide even explains how induction can occur
Oh.
in insulators,
Right.
which I always thought was a bit of a puzzle.
It is a more subtle effect. In most neutral molecules,
Yep.
the centers of positive and negative charge are normally coincident.
Right.
However, when you bring a charged object near an insulator,
Right.
these charge centers within the molecules can shift slightly.
Okay.
One side of the molecule becomes ever so slightly more positive,
Okay.
and the opposite side becomes slightly more negative.
Right.
This alignment of molecular charges across the surface of the insulator creates a net surface charge layer,
Right.
even though the molecules themselves remain neutral overall.
Right.
This induced surface charge,
Right.
although weak, can still lead to an attractive force,
Okay.
which explains why those lightweight polystyrene packing peanuts
Right.
can stick to a charged cat.
So it's like a tiny bit of charge reorientation within each molecule,
Yes.
leading to weak overall attraction.
Exactly.
That mental image of the electrostatic hug is back.
Precisely. And to check your understanding of induction,
Right.
let's look at quick quiz 22.2 again.
Okay.
Objects A and B attract each other,
Yeah.
and objects B and C repel each other.
Right.
Based solely on this information,
Right.
can we definitively determine the charge signs of objects A and C?
This feels like a classic logic puzzle.
Right.
If A and B attract,
Uh-huh.
they could have opposite charges.
Right.
Or perhaps one is charged and the other is neutral and being polarized by induction.
Right.
Now, if B and C repel, they must have the same sign of charge.
Right.
So if B is positive, C is positive, and A could be negative or neutral.
Right.
If B is negative,
Right.
C is negative,
Right.
and A could be positive or neutral.
Right.
Therefore, based on this information alone,
Right.
we cannot definitively determine the relationship between the charges of A and C.
Right.
We'd need more experiments.
Right.
So option E, further experiments are needed, seems to be the correct answer.
You've reasoned that out perfectly. It highlights the nuances of electrostatic interactions
Right.
and the fact that attraction doesn't always guarantee opposite charges.
Right.
Now, having explored the nature of electric charge
Right.
and how it manifests in different materials,
Right.
we arrive at the fundamental law
Okay.
that quantitatively describes the force between these charges. Coulomb's law.
The main event, the ley de Coulomb.
Exactly.
This is where we put a precise mathematical description to the attraction and repulsion we've been talking about, right?
Exactly. It was Charles Coulomb who, through a series of meticulous experiments
Right.
in the late 18th century, using a torsion balance,
Right.
a beautifully delicate instrument, similar in principle to the one Cavendish used to measure gravitational forces,
Right.
and which is illustrated in figure 22.6 of our source,
Okay.
established the fundamental law governing electrostatic forces
Okay.
between stationary charged objects.
The torsion balance.
Yes.
It sounds so elegant.
Right.
Measuring those tiny twists caused by electrical forces.
Wow.
Science is full of such ingenious methods.
Right.
So what did Coulomb discover?
So through his experiments, Coulomb found that the magnitude of the electric force between two small charged objects
Right.
is directly proportional to the product of the magnitudes of their charges
Okay.
and inversely proportional to the square of the distance between their centers.
Okay, let's break that down.
Sure.
Bigger charges mean a stronger force.
Right.
Larger distance means a weaker force.
Right.
And that weakening happens with the square of the distance.
Right.
That inverse square relationship sounds familiar.
Yes.
It's like gravity again.
You've got a great intuition. The mathematical structure is indeed very similar to Newton's law of universal gravitation.
Right.
Coulomb's law is expressed as
Right.
F sub E equals K sub E times the absolute value of Q1 times the absolute value of Q2 divided by R squared.
Right.
Here, F sub E is the magnitude of the electric force.
Right.
Q1 and Q2 are the magnitudes of the two charges. R is the distance between them.
Okay.
And K sub E is Coulomb's constant proportionality factor.
Right.
Our source even notes how precisely the exponent of R has been measured.
Yeah.
It's incredibly close to exactly 2.
And K sub E, Coulomb's constant, that makes sure the units all work out.
Right.
What's its value?
In the standard SI units,
Right.
K sub E is approximately 8.9876 times 10 to the 9 Newton meters squared per Coulomb squared.
Okay.
N dot M squared over C squared.
Right.
Interestingly, this constant is often also expressed in terms of the permittivity of free space,
Okay.
denoted by the Greek letter epsilon with a subscript 0, epsilon sub 0.
Right.
The relationship is K sub E equals 1 over 4 pi epsilon sub 0.
Oh.
And the value of epsilon sub 0 is approximately 8.8542 times 10 to the minus 12 Coulomb squared per Newton meter squared.
Right.
C squared over N dot M squared.
So two different ways to represent the same fundamental constant.
Right, exactly.
Got it. Now, we talked earlier about the elementary charge E.
Right.
How does that tiny fundamental unit relate to the Coulomb, which is the unit of charge we use in Coulomb's law.
That's an important connection to make.
Right.
As we mentioned, the elementary charge E is about 1.60218 times 10 to the minus 19 coulombs.
Right.
This means that 1 coulomb of charge corresponds to a staggering number of elementary charges,
Right.
roughly 6.24 times 10 to the 18 electrons or protons.
Wow.
It really puts into perspective how incredibly small the charge on a single electron or proton is. Even though a coulomb represents a significant amount of charge in macroscopic terms.
Right.
Our source points out that typical static electricity
Right.
we encounter a fraction of the total charge present in everyday objects.
Right. So those dramatic static sparks
Right.
involve a surprisingly small number of